So in the last lectures, we derived the vorticity equation for what we call a barotropic fluid, and that looked very similar to the vorticity equation that we derived in the pressure coordinate system for quasi-geostrophic motion. Indeed, we can, in this lecture, we will derive the dispersion relationship for these Rossby waves that travel in the extratropics. And we can think that we can use both systems equivalently to derive these Rossby waves. Before doing that, before doing this, I just want to discuss with you what other waves there are in the shallow water equation system. And I'm pretty sure you have seen that before. I will now share my screen and open a file, my notes. Can you see these notes here? Yes, nice handwritten. Okay, so this is just a prelude to deriving the Rossby waves, because we will use exactly this system of equation here in principle to also derive Rossby waves. You see, these are the two momentum equations, right? We have seen them already, only that the pressure gradient force here is expressed by the gradient of the height of our barotropic fluid. And it was in principle an exercise for you to show that this is equivalent. The pressure gradient in the fluid can be expressed in terms of the gradient of the height of our fluid. And then we see a third equation here. What equation is this? Let me see if I can draw. This equation here. What is that? Which closes our system in principle. It's the continuity equation, right? Where does it come from? You can derive this by integrating vertically the equation, the three-dimensional divergence, the condition that the three-dimensional divergence is 0. You can write this as a dw by dz is equal to minus the horizontal divergence. You integrate that vertically from the bottom to the top of the fluid. And what you get, using our shallow water assumption again, our velocities are independent of the height of the fluid, then we get exactly this equation here. So this phi is, as you know, g times h for our shallow water model. So this is the continuity equation. It just tells us whenever there is a convergence in our fluid, the height of the fluid has to go up because the mass has to go somewhere. When there is a divergence in our fluid, then the height has to go down. It's just a very intuitive conservation law. Now, we will show today that this set of equation contains also Rossby waves, but that depends on the fact that we apply the rotation operator to the momentum equations. Whereas if we don't do that, these equations support other waves. And I'm pretty sure you have derived those waves already. So the waves that we can easily derive from these are gravity waves. Actually, inertia gravity waves, because we have this effect of the Coriolis force here. So what can we do? We can try to, so you know already gravity waves, right? Because in the first term, you have had the lecture on wave physics. In the wave physics lecture, did you derive gravity waves? Sound waves, perhaps? Yes. Anyway, the important step here is that you are aware of this procedure of the linearization of the equation in order to derive wave-type solutions. And you have done this many times already. So what we can do is, the simplest way to treat it in our case here is to assume for this particular case, we will make a deviation from this when you talk about Rossby waves for a very well-established region. But here, the simplest thing is to assume that the mean state around which we want to linearize is motionless. U bar and V bar is equal to 0. Now we cannot assume that the height of our system, the mean height of our system is 0. There has to be some water in this case in our system, otherwise it doesn't make sense. So the system has a mean height that is different from 0. And this mean height in this set of equations is called HE, some scale height of our system. So this is the set of equations for our inertial gravity waves that we want to, for which we want to derive the dispersion relationship in a linearized way. You know how linearization works, right? We ignore terms that are of higher order in products in the perturbations, essentially, because we can define our initial amplitude u primed, v primed, and phi primed such that they are so small that products of these quantities will be much smaller than all the other terms. And also we have to use the property that the mean state completely fulfills this set of equation also. You're aware of this linearization procedure, right? So whenever there is a term, for example, u primed, let's say d by dx here. Put here, u primed. Then such a term, such a nonlinear term in this equation would be ignored because we can define our initial amplitude such that this term will be small compared to the other terms. We can always set our initial amplitude in a certain way. Then we have to see if our dispersion relationship tells us, yes, the solutions are real. That means our solutions don't grow or don't decay. They are just behaving like waves in this simple case. So we can then assume that for all time, our wavy solution that we define are valid. So this is our linearized set of equations that we can use now to derive waves. Note that in the Coriolis parameter here, we have assumed that the Coriolis parameter is constant. That means the variations of the Coriolis parameter are small compared to this mean quantity. That is the main difference to the Rossby waves that we will derive today, where the variation of the Coriolis parameter is the most important input parameter. Whereas for these waves, inertial gravity waves, the Coriolis parameter itself is important. So what do we do if we have such a situation? As you know, we insert solutions that we know very well. So sine and cosine. This is always the same procedure. We have a linear homogeneous set of equations. We can assume that sine and cosine may solve these equations. So we insert amplitudes A, B, and C, and then the wave, so e to the power, you know, this way of writing sine and cosine just in a concise way. And then we have to insert this in the original equation and calculate the derivatives that are needed. So as you know, the time derivative always gives us, in this case, we have assumed that a wave just propagates in x direction. So there's a wave number k in x direction minus a frequency nu, and then the time here. This is the argument of the wave. So whenever we calculate a time derivative, we get a minus I nu down. So this comes from the time derivative that is on the left-hand side. And on the right-hand side of equations, we get several parameters. So for x, for derivatives in x direction, we get minus ik, in this case ik, and so on. So we get this set of equations, 3 equations for 3 amplitude factors. Now we can write this, actually we can write this in a matrix form. If we identify our A, B, C as a vector, we can write this as a matrix applied to the vector of amplitudes A, B, C equals to 0. And of course, you remember the trick from physics and wave physics. In order to have non-trivial solutions, so one trivial solution of this is, of course, A, B, and C are all equal to 0. That will fulfill this equation. But we are interested in the non-trivial solutions. How do we find non-trivial solutions if we have such a linear equation system? Does someone know? We can require that the determinant of this matrix is equal to 0. Only then non-trivial solution can exist. So the determinant of this matrix has to be 0. And this is what we do. We calculate the determinant of this matrix and set it to 0, because this gives us the non-trivial solution. And you know how, of course, it's a simple procedure how to calculate the determinant of a 3 times 3 matrix. So that's written down here. And if you work this out, you get an equation for the frequency of these waves. Then you can divide this by the wave number in x direction k. That gives us in this case, the square of the phase velocity. And that is equals to f naught divided by k squared plus g times the height of the system. So what we get, if we take the square root of this, is essentially that the phase velocity in x direction is plus or minus f naught divided by k squared plus g times the scale height of our system. Now, if f naught is 0, then this is a pure gravity wave, right? You remember the phase velocity of gravity waves. Now, these gravity waves, for example, if you just for playing around, insert the scale height, a typical scale height for the atmosphere, which would be 10 kilometers, you would come up with a phase speed of 300 meters per second. Now that is way too fast for any weather prediction model to deal with easily. So therefore, these waves are typically filtered out from the equations. And actually, one way to filter them out is to apply the rotation operator to the horizontal momentum equations. Then these inertial gravity waves are not non-existent anymore. They are filtered out. At least it's what we may call external gravity waves. They are filtered out by this procedure, and that is what we see in this lecture. So this is a wave type that exists, that our shallow water equations support, but by using the trick to apply the vorticity operator, the curl, to the momentum equation, we have filtered them already out. So we can try to find Rossby waves without this disturbance of these very high frequency and fast waves. Now I will open the lecture, today's lecture. Okay. Okay, now you see the lecture, right? Mm-hmm. So now we do the same thing that we have just done. We take into consideration for example, the barotropic vorticity equation in the form as it was in 21, which is, let's go back to equation 21. We can use this form in terms of the using its stream function expression, because we have discussed already that this equation is closed as it is, because everything can be expressed in terms of the stream function. We don't need any other information. Or we derive this equation for the barotropic case, actually, that where we have incompressible fluid. On the other hand, we also know that this equation, an equivalent looking equation, is actually valid for quasi-geostrophic motion, which was noting equation 66, where the vorticity can be expressed again as a stream function, a Laplacian of the geopotential divided by F naught. And using this vorticity equation, we come to the same conclusion if we set, if we set this term here, if we cancel this term, the divergence term, that term has to be 0 for our Rossby wave consideration here. It's not entirely true, because when we will come back to this term when we consider the forced type of Rossby waves, but the free Rossby waves that we will first consider, then this term is set to 0. So the only terms we consider is the conservation of absolute vorticity. So we consider the interaction between the absolute and the relative vorticity. This divergence term for the time being for free Rossby waves is set to 0. So then either or, both equations are similar. We can formally use equation 21 for the shallow water model and linearize this. Now, in this case, it doesn't make sense to use a basic state completely without motion. We could do this, but it's more interesting and more useful to use a basic state. As we know, in the mid-latitudes, we have a mean westerly flow. So it makes sense to include this possibility, to have a mean state in this terms of stream function that can be expressed as minus u times y plus a constant. This is our basic state. And this basic state, if you insert this in the original equation, in the vorticity equation 21, it fulfills it, because either there are second derivatives or other derivatives that make this fulfilled. So this basic state, as it should be, fulfills our original equation. Then this has another nice and a property that makes things much easier. So if we apply the Laplacian to this quantity here, This is 0. So that means that the Laplacian applied to the stream function is already equal to the Laplacian applied to the perturbation stream function. So with that, it's clear that the Laplacian occurring in the equation 21 can only work on the perturbation. But that means that this operator here can only be the mean operator, because our linearization tells us that we are only interested in first order linear terms. So the mean operator, advection operator, has to be just a linear term. There would be another term, V bar, d by dy, but V bar, according to our mean stream function definition, is 0, because V bar would be dy bar by dx, and that is 0. So we don't have any mean meridional velocity according to this definition of this mean stream function. And in this beta times v term that we see here, also there can be no other term, because we have to calculate the d by dx derivative in order to express meridional velocities. And there's only the primed quantity. So the linearization is readily done. There's not much calculation to do. This is our linearized vorticity equation, allowing for a mean flow in zonal direction. And now, again, we are looking for sine and cosine solutions. Only to make it a little bit more general, in this case, we allow also waves that not only propagate in zonal, but also propagate in meridional direction. So we say our wave perturbation can have an amplitude, and then sine and cosine waves that are expressed as kx plus, that is the wave, k is the wave number in zonal direction, plus ly, so L is the wave number in meridional direction, minus nu t. So this is the frequency. This is our wave that we try to see if this leads to a solution of this, and if this solution is real. If the solution is real, then there's no growth and no decay of this wave, and under which condition this solution can exist. So again, very simple. We have to calculate the advection operator, which gives us minus I nu, the wave itself, and so on. The Laplacian gives us minus k square minus L square. And this derivative here gives us minus I k times the wave. Then we can divide by the factor a, and we can divide by the wave, and we divide by I. And this is what we get. This is our dispersion relation for Rossby waves that obey this kind of mean flow that we have prescribed. This can be solved for the frequency nu. So nu would be equal to minus u bar k to u bar k minus beta times k over k square, where k square is now the square of the total wave number. Now, it's useful to consider the wave speed in x direction. So if we divide this by k, you know that nu divided by the wave number in x direction gives us the definition of the phase speed in zonal direction. And we look at this relative to the mean flow, then we get this expression here, minus beta over k square. This tells us that Rossby waves, with respect to the mean flow, so assume for the time being the mean flow is 0, then Rossby waves can only propagate to the west in negative x direction with respect, or in general, with respect to the mean flow. But this also tells us that there can be an equilibrium if we bring the u bar on the other side. There can be an equilibrium between the mean flow and the effect of the beta effect. And these two factors, they may counteract each other, which brings us back to the discussion that we had in the last lecture, where the advection of planetary vorticity may counteract the advection of relative vorticity. And when they just balance each other, we get the stationary wave. So the stationary wave is defined exactly when these two terms cancel each other, and we get a phase propagation in x direction that is 0. And the wave number that we can define, the square of the wave number, is then beta over u bar. This is a very important result because it tells us that a stationary, in this case Rossby wave, can only exist if we have a positive mean flow. When there is 0 or negative mean flow, stationary Rossby waves cannot exist. So this is a property that in dynamic metrology and in climate dynamics can be very useful, because we need this mean flow in order for stationary waves to exist. Otherwise, the waves propagate. There's nothing we can do. So this is a very useful quantity. Stationary wave. Then another very important concept is the energy propagation within Rossby waves. You remember very well from your wave physics course that the energy propagation in waves can be derived not by the phase velocity. The phases move, but the energy of wave packets may not move if we consider a wave packet. And our waves are dispersive, so the energy is not just moving with the mean flow, but is moving according to something more complicated, and we have to calculate it. The energy propagation, as you well know from your wave physics course, can be estimated by calculating the derivative of our frequency with k, with the wave number in x direction, and the derivative of the frequency with respect to the wave number in y direction. This gives us the energy propagation in our waves. Do you remember this from wave physics? Now, since the calculation is a little bit complicated, you will do this again as an exercise to show that the result is this. It's not actually complicated. You just have to, you just have to use this expression here and calculate d nu by dk. And you use the product rule of differentiation. And then you can also show, and this is another exercise, that actually it turns out that this is always positive, this term here. So you can show that for stationary waves, for stationary Rossby waves, this term is always positive. That means that stationary Rossby waves, the energy can only propagate in positive x direction, in positive zonal direction. This is an extremely important result, because if we are, let's say we are in Europe and we are asking us, we see a Rossby wave perturbation and we are asking us, where does the energy come from? It can only come from the west. It cannot come from the east. stationary Rossby waves can only, its energy can only propagate into the positive x direction. This is a very crucial, important result also that we find here. So I'm encouraging you to carefully review all these steps here, because this, I promise, is highly relevant for the final exam. So the derivation of Rossby waves is something that is very important, I think, including linearization and so on, which is very simple in this case. So you should try carefully to repeat all these steps that we have done here. Now this is a nice result, because we have shown that Rossby waves, we've assumed they don't grow or they don't decay, and this is what they do, because we found that our nu, our frequency, is completely real. That means our waves just stay there. They don't increase and they don't decay if we don't include any other term. But remember, when we post our initial equation, we have ignored that in reality on this right-hand side here, there may be the divergence term that could cause growth or decay of our Rossby waves. And actually in the next lecture, we will make use of this term. We make this equation, the set of equation, more complicated and make use that there can be a divergence term on the right-hand side, including, that includes vertical velocities. And that leads us to the Baroque instability problem. So our Rossby waves can grow or can decay, taking energy from the mean state and used to increase their perturbation energy. But for that, we need a term on the right-hand side here, which was the divergence term. And we will reintroduce this term in the next lecture. But we also already introduced something similar now, because so far we have been looking at free Rossby waves. So we assume there is a wave perturbation and then that propagates. Or we have a wave package, and then we can investigate how the energy in this wave package propagates. But there's no forcing. But another case is very interesting to look at, and this is the forced case. So we may have a forced Rossby wave. And forced Rossby waves, of course, mean, as you have derived in one of the first exercises, that if our air flows over a mountain, then that means that the absolute vorticity cannot remain constant. There's a forcing for the absolute vorticity when our flow is forced to go over a mountain. So we have to modify our set of equations. So this can become very, very relevant when we are looking at flow over very big mountains, like Rocky Mountains or the Himalayas. Even the Alps that are close by here, they may pose an important obstacle for flow. Now, since we are in a region where we have mostly westerly flow and the Alps are quite thin and more a barrier from the north to the south, the Alps are actually not such an efficient barrier to be a source for Rossby waves. But in cases which can happen that we have strong northerly or southerly flow, then the Alps are very important to modify our flow, because they represent a strong obstacle. But in the mean, since our flow is mostly from the west, they provide less obstacle to the flow. But the Rockies and the Himalayas are so big, they are very important. The Rockies also go from the north to the south, all along the Americas. So the simplest way to deal with this is to go back to an equation that was a little bit earlier, before we derived the absolute vorticity conservation. And we have a more general law, like this equation here, or this equation here. So we have to include something on the right-hand side that causes this divergence, which is the orography. And so we are thinking about, in this case, simply that our flow is forced to go over an orography, and that is parameterized by this right-hand side additional term here. Now we can again linearize the equation in the most simple way. If we assume that the total height of our system is some kind of mean height, let's say the height of the tropopause, minus the height of this topography. And then if we assume that the topography variation is relatively small, the height of our system is always more or less the mean height. So on the left-hand side here, we can replace the total height by just a constant, which is this mean height of the tropopause, which can vary a little bit, but we say the orography variation is so small that the total height is not varying too much. So this any additional term would be of second order. And on the right-hand side, again, we ignore the relative vorticity here compared to the planetary vorticity. And we get this simpler expression here, which almost looks like the vorticity equation that we have linearized before, but with this additional term here. Now, this also means that linearization, this is just a constant. So linearization of this term here leads us exactly to the same expression that we had by linearization, the barotropic vorticity equation. So that is exactly the same thing. So we get exactly the same expression. But on the right-hand side, we have to insert something for the orography. So orography, of course, we can reasonably assume that doesn't depend on time. So there's no local time derivative. Again, the V bar, the meridional mean velocity is 0 in the mean state. And then the only term that can survive from this d by dt derivative is the U bar d by dx of our orography. But now we have to do, we cannot, otherwise it's just an abstract forcing term. So we have to insert something here. Of course, in the real world, that would be some kind of very sharp mountain. But for analytical treatment, that would be a little bit complicated, because we would have to solve a complicated equation. In order for us now to make the treatment similar, feasible, we insert something that is a little bit unrealistic. We insert a sine and cosine type mountain. So the mountain goes on forever. And we want to understand what is happening on top or in the valleys of this mountain. So that's a little bit unrealistic, but makes it easy to solve this equation analytically. We could also, if someone is very good in math, we could insert a more interesting mountain, a Gaussian type mountain, and try to solve this equation. But in order for us to keep it as simple as possible, we want to know if we insert a sine curve here with the mountain height h0, what is the solution that we can find? And we also assume then that we are in a stationary state. So we want to look at the stationary solution over this mountain. Once all the waves have propagated away, and the solutions may become stationary. So the time derivative is set to 0. And then we find, or we can try, okay, let's try a solution that looks exactly like the mountain. And if you do this, you find that, okay, trying this, but using an amplitude that is still arbitrary, an amplitude here, then we find that, in fact, this is a solution if the amplitude of our wave is proportional to the height of the mountain times the Coriolis parameter. So our response will be larger if we have a larger Coriolis parameter, and it will be larger if we have a higher mountain. But then it's divided by the height of our tropopause times, this is the wave number, minus the stationary wave number squared. So it's an interesting feature here. So this means when our wave numbers are high, then the stream function solution is in phase. So if k square is larger than the stationary wave number, then the stream function solution will be in phase with the mountains. So we will have ridges over the mountains. Or if the wave numbers are very small that we consider, then we will have exactly the opposite solution. We have troughs over the mountain. Now, if we look into remember, this was go back to this figure. This is the time mean of our geopotential height. So this is the stream function, if you want. This is our geostrophic stream function that we are looking at here. But the perturbation, we are looking at the zone deviations from the zonal mean. So we see we see these perturbations now that we have just looked at. Just look at the Rockies. Over the Rockies, and this is stationary, this is a time mean situation. Over the Rockies, we find indeed that we have a positive. Now we can assume that, yeah, I tell you that stream function and geopotential, they are proportional to each other. And then, okay, our geostrophic treatment has shown us this. So we consider this geopotential, we can consider a stream function. And so we see that indeed we find a stream function ridge over the Rocky Mountains. And there's a similar feature if you look here over the Himalayas. But of course we have more stationary waves. So other features in the stationary waves may not be only triggered by mountains, but may be triggered by land-sea contrast and more complicated features that we have not considered here yet. But some of these features can be explained by the presence of mountains, where over the Rocky Mountains, we get this permanent ridge feature. And then perhaps the mountains, also the mountains in the Greenland region may be relevant, but then it's not so clear that we get a ridge or a trough over there. But for the Rockies and for the Himalayas, it's very clear we get ridges. So there is a problem, of course. The problem occurs when in case our wave number is exactly the stationary wave number, then this term vanishes. If this term here vanishes, if k square is equal to ks square, our amplitude becomes infinite. And this is what is called resonance catastrophe. So we have looked at we are looking at a forced system, but there's no damping. So we have just the mountain forcing, but in the atmosphere, we have assumed everything is, we have considered the Euler equation, if you remember from the beginning, no friction, and so on. So we can have this effect of a resonance catastrophe when our waves are exactly like the stationary wavelengths. You can avoid this by inserting some damping into the equation, in which case the amplitude will not go anymore to infinite. But otherwise, this is a logical outcome of our treatment. What we see here is something that we will discuss at much more length later on in this course. I just want to highlight that there can be other sources of forced Rossby waves. One very, very important way to force Rossby waves are the mountains. Another important source could be tropical heating. So tropical heating could be relevant to cause stationary Rossby waves that we have just seen, that are there in the time mean situation. So inhomogeneities and tropical heating, because they will generate an upper level divergence. And this upper level divergence, as is the case for the mountains, will be a source for Rossby waves. But we can also assume that there's a El Nino phenomenon going on, so some anomalous convection in the Eastern Pacific, and that in some winters may send out a stationary Rossby waves that influences climate in North America, in Europe, and in other regions. So these are all possibilities for how Rossby waves can be generated in the exotropics. Topography, tropical heating, and also heating in the Rossby waves themselves, because for the time being, we have assumed that they are completely dry. But in reality, if we take into account, for example, moisture processes, then that will also be a reason to lead to vertical velocity and so on. So I will just lead to to tell you what exercises you can actually do for the next lecture, and the ones that I don't encourage you to do. So exercise number 1 is very useful. I encourage you to do, as is exercise number 2. Exercise number 3, I think, is also very useful. It's transforming our problem into a real ocean problem for Rossby waves. But then I don't want you to do exercise number 4 and not exercise number 5. Exercise number 5 you may actually read and study, because it's quite interesting. It encourages you to write a model for a Rossby wave in an extratropical beta channel. And that if you do that, you will see that waves, in this case, it's actually, again, a forced wave, because we assume that there's a mountain range that causes our wave. And then you can study what is the response of the flow to this mountain forcing in this channel. It's interesting to do, but it turns out to be very complicated, because you should discretize the nonlinear version of the vorticity equation, including a damping term, which otherwise having given that is a nonlinear system, solutions may explode. But then the problem is that at some point, in order to get back to you can calculate the velocities and so on, but in order to get back to the stream function, you would have to invert the vorticity. So once you have calculated the solution by advancing in time the vorticity, at some point, in order to find the stream function, you will have to invert the Laplacian of the stream function in order to get the stream function back. And so that's in order to to do that, you would either have to use transformation into spectral space, or, as I suggest in this exercise, to do some kind of Gaussian elimination between two boundaries. Anyway, if you read this, it's in principle an interesting exercise, but it turns out to be quite complicated, as you can see. Already the discretization is very complicated. But if someone has interest, I would collaborate to solve problems if there's a problem to solve this equation. It's a nice exercise, but I don't say you should do it. But if someone is interested, you can do it. So just an outlook for Monday's lecture. I think today we will then just finish earlier. I don't want to go into this. But on Monday, we will discuss the problem of the baroclinic instability. So how now these Rossby waves, for which we have derived now the dispersion relationship, that according to their wave numbers, they can propagate in positive x direction or negative x direction, or can be stationary, but they cannot grow or decay according to the system that we have considered now. But we have to do something, and you can see from equation, this is equation 103 here, what we will do is we have our vorticity equation, the same that we have used today, but on the right-hand side, we allow the presence of the divergence, or equivalently the omega, the pressure vertical velocity by dp. And that makes, so far we didn't have to consider any thermodynamic, but this occurrence of the d omega by dp makes this vorticity equation coupled to the thermodynamic equation. So we have not a closed system if we just consider the momentum or the vorticity equation. In order to close that set of equation, we have to use another equation, which is the thermodynamic equation. And so this interaction between dynamics and thermodynamics gives us the possibility then to find this Pyroclinic instability, which we will derive in the next lecture. I think for today, I'm finished with this. So I encourage you over the weekend to try to do some of the exercises which I have told you can do. And if there's any problem, on Monday, I think it's a good occasion for us to discuss some of the exercises. If you have doubts, it's better to ask. Okay?
Okay.
All right. So do you usually come to current weather?
Yes.
Okay. So I see you then at current weather today.
Okay.
Okay. All right. Bye.
Bye.
Bye.